What if I told you that 5G has a secret language, a kind of hidden rulebook it uses to be both incredibly fast and unbelievably flexible? Well, it does. It's a concept called numerology, and it is the hidden genius behind our entire modern network.
So, let's start with the big puzzle 5G had to solve. Think about it. How can one single network give you a solid connection when you're out in a huge open field and at the same time deliver insane speeds to 50,000 people packed into a city stadium? I mean, these two situations are complete opposites. The secret? It's all about the network's ability to basically change its own rules on the fly.
So yeah, how does one network master two totally different worlds? Well, the answer is in that secret language we mentioned, and that's exactly what we're going to decode right now.
Okay, so this big idea is called numerology. And no, forget astrology, this isn't about your star sign. In wireless engineering, numerology is this super powerful, super flexible rulebook. It's basically a bunch of numbers, parameters, that 5G can tweak in real time. It literally changes the shape of its signal to be a perfect fit for wherever you are. That right there is how we solve that whole stadium versus field problem.
All right, to really get how this rulebook works, we kind of need to pop the hood and take a look inside. So let's start with the most basic building blocks of a 5G signal.
So, the technology at the heart of all this is called OFDM, and the best way to picture it is to think of a highway. Imagine trying to send all your data down one massive, super fast lane. One little accident, some interference, and boom, the whole thing grinds to a halt. OFDM is way smarter. It takes that one big stream and splits it up into thousands of slower, parallel lanes. This makes the entire system way more robust and less likely to crash.
But of course, there's always a catch, right? In the real world, that radio signal doesn't just travel in a nice, neat, straight line from the tower to your phone. Oh no, it bounces off everything. Buildings, trees, cars, you name it. This creates echoes. And these echoes are a problem because they arrive at your phone just a little bit later than the main signal. This causes the little packets of data, the symbols, to kind of blur together and create errors. It's pretty much the digital version of a multi-car pileup on that data highway.
So how do we fix this? With a really clever engineering trick called the cyclic prefix, or CP. The easiest way to think of it is like a small protective bumper that gets added to the front of every single data packet. This little buffer is just a copy of the tail end of the tacket, and its whole job is just to sit there and absorb the impact of those late arriving echoes. It's a sacrificial lamb, basically, that protects the actual data from getting messed up.
Okay, now, here is the single most important point. You've got to remember this. The bigger the cell, the area one tower covers, the farther those echoes have to travel. And if they travel farther, they take longer to arrive. So a longer travel time means you need a longer cyclic prefix to protect the data. Make sense, right? A bigger area needs a bigger bumper. This direct link between cell size and the bumper size, it's the key to this whole thing.
Okay, so we've got the basic rules down. Now, let's have some fun with it. Put on your engineering hats for a minute, because we're going to see how all these numbers actually come together when you design a real 5G system from the ground up.
Now, I know this looks a little intimidating, but the idea here is actually super simple. Let's say we have a 100 megahertz chunk of radio spectrum to play with. We have to make one single numerology choice right at the start. How far apart do we want to space our little data lanes? Let's just pick a number, say 30 kilohertz. Okay? That one choice now creates a domino effect. It dictates everything else. Based on that 30 kilohertz, we do the math and find out we can fit about 3,300 of those lanes in our spectrum. But for computer chips to work efficiently, they love numbers that are powers of 2. So we just round that up to the next convenient number for the hardware, which happens to be 4,096.
And now for the magic. When we multiply our 4,096 lanes by our chosen spacing of 30 kilohertz, we get this very specific, very important number, 122.88 megahertz. And trust me, this is not a random number. In the world of 5G engineering, this is what you might call a sacred number. It literally defines the precise clock speed for the chips that run inside the cell tower and inside your phone. It's the perfect example of how that one tiny numerology choice at the beginning ends up creating this whole cascade of critical design decisions.
So we've established that 5G can change its numbers. But the big question is, why does it even need to? Well, that brings us to the two completely different worlds that 5G has to operate in, often at the exact same time.
You see, 5G operates in two main frequency zones. First, there's what we call FR1, or sub-6 GHz. Think of this as the marathon runner of 5G. It might not be the absolute fastest, but man, it can go the distance. It's perfect for covering huge areas, like entire cities or big stretches of the countryside. And then you have FR2, which is millimeter wave. This is the sprinter. It is blazingly, unbelievably fast, but it gets tired really quickly. It can't go very far. So it's perfect for very specific, crowded places like a stadium or a super busy city block.
Okay, this is it. This is where we connect all the dots. We've talked about the problem of echoes, the solution, which is that cyclic prefix bumper, and we've got these two very different worlds, the marathon runner and the sprinter. Now let's put it all together and see why this flexible numerology thing is 5G's real superpower.
I mean, it makes sense, right? A marathon runner and a sprinter face completely different challenges. They train differently, they run on different tracks. It's the same for 5G. The physics involved in covering a massive, wide area are just fundamentally different from the physics of delivering insane speeds in a dense, tiny area. You just can't have one rigid set of rules that works perfectly for both. It's impossible.
And here we go. This is the big aha moment where it all clicks into place. Let's start with FR1, our marathon runner on the left. What's its biggest problem? Huge cell sizes, which means really long echo delays. The fix? Well, we know this one. It needs a longer cyclic prefix, a bigger bumper. Now here's the genius part. To get a bigger bumper, 5G does something that sounds backwards. It chooses a smaller spacing between its data lanes. A smaller spacing actually makes each bit of data last a tiny bit longer, which gives you more time to create that bigger protective bumper. Okay, now look at the right side, FR2, our sprinter. Its problem isn't really echoes, because the cells are tiny. Its problem is something called phase noise. It's like electronic static that's worse at these super high frequencies, and it can cause the data lanes to bleed into each other. The fix? It's so simple. Just create more empty space between the lanes, and you do that by choosing a larger subcarrier spacing. You see? Two totally different problems solved by two totally different numerology choices. It's a perfect match.
So what's the big takeaway here? It's this. 5G is not a one-size-fits-all network. Not even close. It's more like a chameleon. It intelligently looks at the situation it's in and uses this toolbox, this numerology, to completely change its own rules so it can be the absolute best network for that exact moment in that exact place. And that right there, that ability to be both the marathon runner and the sprinter, that is 5G's true superpower. It's the reason this one network can connect literally everything from a tiny sensor on a remote farm all the way to a full-blown virtual reality headset in a packed-out arena. And that really leaves us with a big question, doesn't it? When you have a network this smart, this adaptable, what kind of future is it going to build?